Archie is a portable 64-core system made out of 18 individual Raspberry Pis and is being used for outreach and education. This small cluster shows the idea of high-performance computing by resembling large supercomputers like the UK's National High Performance Computing Facility Archer. The LEDs on the front of each Raspberry Pi shows the CPU, network load and the temperature of each core as it runs. Monk is a state-of-the-art weather forecasting model developed by EPCC and the UK Met Office. It can simulate the atmosphere at a very high resolution, covering tens of meters. It was built to run on thousands of cores on supercomputers like Archer, but can also run on small systems like Archie for outreach purposes. When we start the simulation, this black screen appears. This is where the demo's visualization will eventually appear, but first we need to select a few settings. Up in the top left corner of this window there are two drop-down menus, and within File there is a Settings button that will allow us to open the new interactive settings window. When this window opens up, you will see there are two tabs, Basic and Advanced. Under the Basic tab, a map of the UK and Ireland is shown. The 5 icons you can see in this map are linked to a live Met Office data feed known as DataPoint. This is a service to access freely available Met Office data feeds from hundreds of weather stations all over the UK in a format that is suitable for application developers. The icons' images relate to whatever weather this data feed is saying. So a picture of a cloud relates to cloudy weather, rain to rainy weather, and sun to sunny weather. Also, being able to access live weather data means we can feed this data into the simulation and simulate the weather as it is right now. So the 4 icons over the UK are positioned in the Highlands, Edinburgh, London and Cornwall. This positioning is to give the demo the option of different landscapes to simulate the weather over. So if you click on the icon in the Highlands, it will create a mountainous landscape. If you click on the icon in Edinburgh, it will create a city next to the sea landscape. London, a city with a river running through it, and in Cornwall, land and sea. Now, when we go to the Advanced tab, we are given the option to change many more settings towards the simulation. We can select input parameters like wind power, temperature, atmospheric pressure, time of year and water level. This is to allow us to see how changing the input parameters can change the weather. Other parameters influence the performance of the simulation. Number of cores per node to use, number of cores to split up the workload in width and in depth. These determine the decomposition method and affects network load. Okay, now let's start a simulation, and by click and play we can watch it evolve with time. While the simulation is running, clouds and rain are rendered in real time, using meteorologically accurate data from Monk. We will see the forming of clouds and how rain is starting to fall. The plot at the bottom of the visualization shows the ratio of computation and communication time for each core. Green is computation and red is communication. So for this simulation, only one core is used, and hence the time spent on computation is much greater than the time spent on communication. Whereas if more cores are used, the code will spend more time on communicating between each core than computation. Therefore, we want to spend as less time as possible communicating while increasing the performance. The optimal decomposition strategy has to be used. We are now also able to see the temperature profile of the cloud and rain system. This gives us a whole new outlook into the temperature of different parts of the atmosphere as the clouds form and the rain begins to fall. A useful feature of this is that we can switch between the temperature view and the real world view during the simulation to see what parts of the atmosphere and clouds are associated with high or low temperatures. We can also see the pressure profile of the system. However, throughout the course of the simulation, nothing much seems to change.